Hello, y'all. Welcome to lesson 139 of my DB chemistry curriculum. Today we're doing structure 3.2.9. This is an HL topic. We're going to discuss infrared spectra, which can be used to identify the type of bond present in a molecule. We'll interpret the functional group region of an IR spectrum using a table of characteristic frequencies based on the wave numbers measured in centimeters inverse. We will include reference to the absorption of IR radiation by greenhouse gases. We'll do that at the end. And we'll use our data booklet for interpretation of IR spectra. That's going to be section 20 of the data booklet. So make sure you have that handy. So let's start off with what is infrared spectroscopy. Now, we already know infrared radiation is part of the electromagnetic spectrum. It comes before red, infrared before red. But basically, we use the IR radiation to determine bonds present in molecules. But like, how does that actually work? Well, turns out that different bonds, and all bonds are quite different, but different bonds absorb different amounts of IR and different wavelengths of IR as well. And when they do that, they vibrate as well. When they absorb different amounts of IR, they can either stretch or bend, and we referred to this as modes of vibration. We will discuss this a little bit more as we get to the greenhouse gas interpretation of infrared radiation, but for now, we just need to know that they will absorb different amounts and wavelengths of infrared and react differently based on that, or interact differently. So when we do this, we get a spectrum. So spectrum is produced by measuring IR absorbed. And that's it. When we have that spectrum, we will use a list of known values to identify the molecule. Identify molecules. So that list of known values is in your data booklet. It is specifically section 20. I'll throw it on this page. We'll look at it in a minute. Um, Section 20 of data booklet. So let's take a look at this list. Now, we'll zoom in on a couple aspects of it. Let me just lock in place. So you'll notice it has a lot of different classifications. You have your iodoalkanes, your bromoalkanes, and you'll see that it's measured in wave number. We'll discuss that in just a moment, or actually, I guess we can do it right now. Wave number is just 1 over the wavelength of infrared. It's in centimeters inverse, as you can see there. Um, that's what we measure on our x-axis of these spectrums that we produce. We also have intensity. Intensity is a measure of bond polarity. Bond polarity. So you'll notice our halogenoalkanes have a strong intensity, as we'd expect with a lot of bond polarity. We have weak bonds when we have these alkenes, where it's carbon-carbon, very low polarity. So we have very strong ones with our hydrogen bonds. So that's what intensity is kind of classified as. Now, we have all these lists of numbers but really we're only going to focus on everything after 1500 wave number. And we'll discuss that as we look at a graph. So let's take a look at what one of these spectrums actually looks like. All right, so I have an unlabeled diagram right here, but we'll notice a couple things. Lock that in. So right off the bat, we notice that we have these peaks and valleys. So we have our transmittance here on our y-axis, and transmittance is anything less than 100% is absorption. So if the bond is absorbing infrared, we're going to see that as a dip, a valley in our graph because it's absorbing this radiation. So we have less transmittance, light is not being transmitted through. And you'll notice it's percent, so we of course have decimals. Also, as we see our wave number, you'll notice it increases going back. It is an inverse. So we actually will take these graphs and divide them into two regions. And if you draw an imaginary line at 1500, so 1, 2, 3, 4, 5, this is our two regions. This is what we call the fingerprint region. And it's less than 1500 centimeters inverse. The fingerprint region pretty much is unique to the compound. That's why it's called fingerprint region. Unique to the compound. So every molecule is going to have its own very specific fingerprint region. Now, here's the thing. We are not going to focus on that region in the DP curriculum. We're actually going to focus on this region. So greater than 1500 is what we call the functional group region. And exactly like the name, we can identify functional groups in molecule. So that's what we're really going to use our data booklet for. You're never really going to look at anything less than 1500. This is basically the only thing we're focusing on. So let's go ahead and try and identify the functional groups present here. Now, what I'm showing you right now is specifically a 2-carbon chain. I know what this is, but let's go ahead and see what functional group is present on our 2-carbon chain. And you'll notice I deleted some information. So we have this first region right here, this valley right below 3000, around 2900. So what is a sharp downwards peak? Well, let's go ahead and look at our chart. We're looking for 2900. So it could be this carboxylic acid, but it's a strong, very broad area. It could be this, alkanes, alkenes, arenes. So this one would actually represent this strong peak right here. This is a carbon-hydrogen bond. This is our carbon-hydrogen bond. So generally, we're going to see a carbon-hydrogen bond around 2900. That's usually what we see. It can be a little below and a little above, but generally that's it. Next, we have this very smooth valley, somewhere between 32 and 3400. So what might be that? Well, there's only one thing that specifically fits between 32, 3400, and it's kind of that broad valley, and that's alcohols. Alcohols and phenols, very specifically that hydrogen bonding. You'll notice we have other hydrogen bonding up here, but it's weaker. It's or not weaker, it's a lower wave number. And so this is very much an OH bond associated with an alcohol or phenol, but I told you it's a 2-carbon, so we can assume it's not a phenol. So in this case, our OH around 3200 to 3400. So this is going to be an OH bond. Therefore, I know that this compound, being 2-carbon, is actually ethanol because two carbons with a single OH bond is going to be ethanol. So let's go ahead and try this now, looking at a brand new compound. And this compound is going to be, again, a two-carbon compound. All righty. So go ahead and lock it again. So this time we have two new peaks that I have highlighted here. We'll first divide our graph so we're not looking at anything under 1500. Again, we're only going to focus on the functional group region. And we have this first peak right around 1700. So at 1700, what are we seeing? It's a sharp peak. So what we can do is I'll actually just bring up the chart again, so I'm not scrolling over and over and over again. So at 1700, we only really have one thing, 17 to 1750, and that is a C double bond O associated with aldehydes, ketones, carboxylic acids, and esters. So 17, 1750, it is kind of right in that middle zone. That is our C double bond O. All right. Now, as we move forward, let's go ahead and look at whatever the heck's going on over here. So we now have kind of this broadish, shaky peak, and it's a bit broader than our other alcohol before, but it's lower than our other alcohol. It's kind of in the range of like starting at around here and ending around here. So about 25 to 31. And when we look at our graph, that is our OH specifically with carboxylic acids. So right here we have OH at around 2600 to 3000, or more like 3200. And so if we have a C double bond O and an OH specifically with carboxylic acids, we can assume that this is a C double bond O OH or a carboxylic acid. Specifically, we are looking here at ethanoic acid. Now, a question you might have is, why does this OH change so much? Because in our ethanol, it was this nice smooth curve, but in ethanoic acid, it is a very sharp, jagged curve. We get like these horrible peaks that are not as low. They're letting more light through. It's only about 80% absorption. So what's going on here? Well, when we look at ethanoic acid or a C double bond O compound, sorry, carboxylic acid compound, this OH, very different than our ethanol. This OH is now bonded to a carbon that is bonded to an oxygen. So the dipole moments are very different. So very much this proximity to the C double bond O affects the OH peak. And so we have a full different region for that alcohol when it is with a carboxylic acid. Because again, that dipole moment, which is what this intensity is measuring, is very different when that carbon has another dipole with a double bond oxygen. All right, so let's go to our last image here, our last example. And I've identified a couple peaks as well. And I'll go ahead and insert our chart back. So in this new one, we have this down by the 1750 again. So we already know that this is going to be a C double bond O. Furthermore, we have this peak that's kind of sitting in the range of 27 to 2900, but it's not expanding past 3000 and it's not very broad. We've seen that one before too. That is just our CH, our alkane bond. So in this case, we have a double bond O and an alkane bond. Again, we're dealing with a two-carbon compound because I'm trying to keep all these examples consistent, meaning that there's only one possible option for this. This is going to be an aldehyde. So we have, it can't be a ketone because again, it's two carbons, no matter which one it is, it's on the end. But basically, we're looking at a carbonyl group. And you might notice this CH is also a little different than what you'd expect, but of course it is because it's a carbon that also has a double bond oxygen, so that intensity changes a little bit. And so we're going to very much see that kind of a little more spread out, not as sharp peak as we saw before. So this is kind of how we identify the functional group region of compounds based on IR spectroscopy. This is a skill that you should try and practice as you continue setting for the DP exam. With all this said, let's move a little bit into IR and greenhouse gases. Greenhouse gases. All right. So, what is a greenhouse gas? Hopefully, you have some idea that of what they are, being a DP chemistry student, just knowing a little bit about the world. But this is a gas that absorbs IR. Not only does it absorb IR, it can also re-emit it, but this is going to perpetuate the greenhouse effect of keeping more infrared radiation trapped in Earth's atmosphere, slowly heating the Earth, what we've come to call global warming and now expanded into climate change. So, what really affects this? Well, this is where we start classifying compounds. And basically, this is all based on the dipole moment of a compound. And whether that dipole moment makes the compound IR active or IR inactive. IR active meaning that it will absorb infrared, and IR inactive meaning it won't absorb infrared. So we can see multiple compounds can be IR active or IR inactive, and this is where we come back to those modes of vibration. So let's take a look at CO2. Most of us know carbon dioxide is in fact a greenhouse gas. But when we look at the compound, it actually has two modes of vibration. It can perform symmetric stretching, but it can also perform asymmetric stretching. And the question is, which of these modes is going to be the IR active mode? Well, most of you know just from a diagram that carbon dioxide is not a polar molecule. The dipole moments between the oxygens cancel out. However, when interacting with infrared, and when the molecule stretches, it can stretch symmetrically. When it stretches symmetrically, those bonds will continue to equal out. It will continue to not exhibit this overall dipole moment. And therefore, when it's doing symmetric stretching, this is actually inactive. However, if, for instance, the bonds extend on one side and shorten on the other due to asymmetric stretching, so they bounce around, then our dipole moment shifts. So as the bonds stretch, to different lengths, the dipoles no longer cancel. Therefore, this is going to be IR active. So this is how CO2, a nonpolar molecule, can still be active in absorbing infrared radiation and participating in the greenhouse effect. Let's look at another molecule that people forget is actually a very potent greenhouse gas, and that's H2O. So what makes it such a potent greenhouse gas? Well, with its bond shape and the molecular geometry, even if it stretches symmetrically, so symmetric, or if it stretches asymmetrically, oops, we'll notice that it is still polar. And so both of these are going to be IR active, but water actually has a third mode of vibration, which I briefly mentioned. It has bending. So these bonds kind of bend up and that oxygen moves down. And yet it still remains asymmetric and it still remains a polar molecule. So water is always IR active. The last compound that the DP wants you to know about and think about is methane. I'm not going to draw all of methane out, but methane can undergo both bending and asymmetric stretching. Therefore, we can understand that this is IR active and contributes to the greenhouse effect because it can do both of these kind of um, changing of their dipoles to be active. The last part of this are diatomic elements. So diatomic elements actually have no dipole moments. And because they have no dipole moments, uh, they can only really have one vibrational mode, which is symmetric stretching, while still not creating a dipole moment. So we know that this is IR inactive. And that's about it for this. And honestly, that's pretty good for us because considering most of our atmosphere is diatomic elements of oxygen and nitrogen, it would be really bad if they suddenly were IR active and absorbing all that infrared radiation. Anyways, I hope this helps you understand a little bit more about infrared radiation, how we use it as an analytical technique, and how it affects the world around us. And have a